and grade of the college in the coming NAC accreditation process. These international sessions are occasions that lead the students in the path of new knowledge. The resource person of today's online lecture series is Dr. John Joseph, consulting geoscientist, Morley, Western Australia. Dr. John Joseph took his bachelor's degree from Kerala University and master's in marine geology and geophysics from CUSAT, Kochi University of Science and Technology, with first rank. He had his PhD at Ocean Research Institute, University of Tokyo, Japan. The time is from 94 to 98. And a postdoctoral researcher, that is a postdoctoral research qualification at Geological Survey of Japan, AIST, Tsukuba, Japan from 98 to 2002. Joined as senior lecturer in geophysics at CRC, LEME, University of Adelaide in the period of 2002. And from 2002 to 2007, he was there. And later moved on to the UTS, Geophysics, AeroQuest, Perth, as his principal geophysicist. And from 2012 to 16, he was there. He worked as a principal geologist of the geophysics ground probe based in Malaya, Western Australia, and from 2016 onwards as consulting geoscientist in Morley, Western Australia. He also holds a MBA from Edith Cowan University, Western Australia. He also has many awards and recognitions, including Young Scientist Award from Indian National Science Congress, that is in 1994, Monbusho Scholarship from the Ministry of Education, Japan, NEDO Fellowship, Japan, JSPS Fellowship from Japan, Wissing Research Fellowship, Tokyo, and among the Dean's list of highly accomplished graduate of School of Business Management, ECU, Australia. Other than all this, he is also a classmate and dear friend of our Professor Davis. So we are honored by your gracious acceptance, your distinguished presence, and look forward eagerly to your eloquent words of wisdom as a resource person of this webinar. Okay, welcome to Sir to Sahardaya College, and also thank you very much for the presence here. I wish this lecture series all success and extend on behalf of the Sahardaya College warm greetings to all the delegates, teachers, students from other institutions and from Sahardaya College. Thank you. I conclude.
Thank you.
Well, thank you, sir, for your wise words, and I welcome our special guest, Dr. John Joseph, who is an eminent consulting geoscientist at Morley of Western Australia, for the talk on an investigation of hidden water resources using airborne electromagnetics. I mean, how cool is that? And I'm sure each one of you are thrilled and excited, just like me, to hunt down those hidden water resources. So please.
Thank you, Aisha. And thank you, Dr. Matthew Kent, for the nice words. And also to thank Professor Davis Jacob for inviting me for this online series. And I think I can start by putting some slides on it. Am I right, Aisha?
Yes, sir.
Yeah,
please.
and begin. Give me a minute. Are you able to see the slides by any chance?
Oh, old memory. You're starting with old memory.
Yes, I'm going to start with that. I thought that's the best one to start with. All right, okay. So here I'm actually going back to 1986, 37 years ago, isn't it? And there's a photo which we have taken while we are visiting, as an MSc students, we are visiting Indian Museum, Calcutta. And here you can see your Professor Davis over there. Can you see?
Yeah.
And also, of course, I'm behind it. Right. So that actually gives me a long memory. and we had the opportunity to
But
meet.
one guy, Mr. Nandan, was missing now.
Yes, Nandan, who is next to Davis and me, he was a geologist with the Department of Geology in Government of Kerala, and we are actually missing him. He was called by God a few years ago. We remember him. And of course, others are there, few people from different departments and different organizations currently working on, and some of them are overseas as well. Okay, so we get into the talk, and I could see that from the list of the talks which you had in these 4 days, like you had started with the submarine groundwater discharge along the coastal zones of India from Dr. Suresh Babu from CES, and then it goes up to the space like GPS application of Earth Sciences by Dr. Sunil. And then again, you came down to the ground with cratonic blocks and mineralization by Dr. Pradeep Kumar from Kerala University. And now we are going slightly up to the airborne side. And tomorrow, I think you are going further up to the remote sensing. Right. Anyway, thought of looking at it. And let me start with that. So the title, as Aisha mentioned, is an investigation of hidden water resources using airborne electromagnetics. And I put this one because my main intention was to share with you the application of the airborne geophysics with you. But when we are looking at the airborne geophysics applications, it's always good to have some case studies along with that. And again, airborne geophysics itself is a wide topic. So we need to restrict, at least for this talk, I need to restrict to just one of the methods. That's the reason I put this one. I'll go further. And just an overview of the talk, today's talk, and hydrogeological settings of that area of survey will be discussed. And also we'll be discussing on the airborne surveys and the data processing ways, not in a very detailed way, but in a very brief way, and also data inversion and results, and how you compare with any a priori information available, and also how you do the interpretation and the conclusion. And also I want to challenge the students over there with some data set available for Indian side, which you can work on. Okay, so let me go further with that. If you look at this image, you would see that the airborne, the accessibility or the unlimited accessibility of the airborne measurements. You think about a forest, thick forest. When you talk about thick forest, probably in Kerala, we may not have that much of thick forest over there. Because mostly, urban land, and of course, in the Western Ghat we have, but we don't know much about it. If you get into that, we don't know how we can do any survey over there. And think about a marshy land. In our own coastal region, we have the mangroves over there, or think about any area in Indonesia, in Africa, or in deltaic zones of Brazil and all over the world. So we have lots of places which is still not surveyed properly. Similarly, we have deserts, the African deserts, and deserts here in Australia. We have vast desert over there. The image shown over. Can you hear me? Okay.
Yes, sir.
The image over here which shows there's an desert from Australia. And even in 16th century, when the Dutch people came in onto the western coast of Australia and looked around, they could see just vast land, no man's land over there, and they were not so happy to settle in there, and they went back. That is the sort of land over here, the deserts, and also you think about Alaska or Greenland and places in Siberia where you have the ice-covered region. Lots of area which is still uncovered. And which is still yet to be surveyed properly. So these airborne methods can have the large acquisitions, speed, very high speed acquisitions, and also it can get onto the frontier areas such as forest, desert, marshy land, also icy land or waters. And of course, since we are on the aircraft, we can do the acquisition very quickly. That's an advantage of that. So let me go further with that. And when we look at the airborne geophysical method, I have listed 4 of them here. One is airborne magnetics, which is pretty common in India too at this moment, and airborne radiometrics, and airborne gravity and gravity gradiometry, and also airborne electromagnetics. So the 4 different systems have been using for, in all over the world. And today we would be concentrating mainly on the one which is the electromagnetics. That's the electromagnetic induction is the basic physics behind it. And when you look at it, probably some of you already knew about this Gauss laws, Faraday's laws, Ampere's laws, Lenz's laws, and Maxwell's equations. I don't want to put any equations over there because this is a very brief talk. So just if you are curious, you may read through that, all these different laws. I'm sure that in undergraduate level, many of the undergraduate courses, especially physics, you would be learning more about it. And the only thing what I want to remind you about is that when we talk about the electromagnetic induction, we talk about the right hand thumb rule, right hand palm grip rule. So where we have, if the current is passing in the thumb direction, then there's a magnetic field is being created in the grip area. And if the magnetic field is created like that along the grip, then what happens if the current is being changing, then the magnetic field also changes, and the change in magnetic field on the grip one again creates another current. And the changing current again creates a secondary magnetic field. So that's a sort of combination of.
It is not audible.
Is not audible? All right. Can you hear?
Okay.
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 Yeah. And I have put an image over there. You can see that the grip rule over there, and the magnetic field is being created around it. And this changing magnetic field around it can give rise to another electric field, that's current. And that current can create a changing magnetic field. So that's the electromagnetic induction in briefly. So that concept can be used for different purposes. And that can be clearly being used in airborne geophysics and airborne electromagnetics. So let me go further with that. Here there are some systems, airborne EM systems, mainly the time domain EM systems over there. And the one on top is a famous Fugro system, that's a CGG system currently. You can see around the wings of and the tail and the bow of the aircraft, there's some winding over there, some wires are passing. Can you see that? And that is actually the transmitting area. And again, you can see 2 things over here, one over here and one there. And this one, what I'm showing right now, is the receiver for the EM responses. And this is actually a magnetic sensor. And we can fly by having the birds over, it's called as birds. So birds can be tied up to that one, and that can be recording all this data, and it can fly around, and we can have the survey done like that in a fixed wing aircraft system. Similarly, another system over here is a spectrum system. You can see the bird over there, small bird. And another way is putting a rectangular shape transmitter receiver system on below the helicopter. And another one is that we can hang a big loop of wire over there, and with the receiver in the center of it. And again, another one is a different shape over there, hexagonal shape. And again, we can see another one. And when I say about these a few different types of airborne EM systems, most of them are being used in India as well. And I know there are airborne EM surveys by different companies, and different departments of government of India has done by this system. That's the CGG's system, this mega-TAM system. And also Department of Atomic Energy has done surveys with this system and that system. And NGRA and government of Gujarat has done the survey with this system, definitely a few years ago, because I had the opportunity to be a part of these surveys and the data processing and interpretation at some stage. And I'm going further. Here is shows the summary of how efficient these helicopter-borne systems are when you compare with the fixed wing systems. And you can see it can fly very low altitude. It's about 30 meters. The so-called bird would be around 30 meters above the ground. And then we can have high powers there. When I talk about this one, BZ means the vertical magnetic field is actually high moment over there. Okay. So again, and just going to the next one. Here, what we are doing, we have a system like that. Can you see that system over there? This transmitter loop over there. This transmitter loop, we can put a current through it. We have a generator attached with it, is right here, and we can pass a current through it. We can pass a big current through it, and when the changing current is going through that one, that creates magnetic field. Again, you thumb rule, the grip rule over there, you know that how the magnetic field is being created in that, when the current is passing through this one. Okay, so when it passes through that one, it keeps on going and creates the magnetic field, and that will be going down and down to the earth because the air column is there. And once if it touches the ground, as you see here, this way, you can see that the magnetic field which is going down and down through the earth will attenuate. That means that the magnitude of the magnetic field will be reducing, keep on reducing, depends on the type of rocks or the soil present underneath. And if the magnetic field going down through like that, if it is changing over there, that would create an eddy current. And the changing eddy current creates a secondary magnetic field, and that can be recorded with a receiver over here. So what we measure is a combination of the transmitting moments plus the responses from the ground. But we are sure that we know what is the transmitting moment or transmitting charges over there. So if we know the transmitting current over there, we can remove that easily from our data processing. And what you are left with is the responses from the ground. And if we know the responses from the ground, then we can work on that responses. Depends on how it is changing as the time goes. And that is actually being shown here. You can see that there is a transmit on-time measurement over here. You can see that there's a transmitter current is a square-shaped current is being passed to that one. Then again, it's off time there. Then another square type over here. Then off time there. Then another is keep on going like that in every few seconds. And these measurements over here is done in every few milliseconds. So every few milliseconds, we can see the change in magnetic field, what is being measured here on the secondary magnetic field. And that can be used for studying the Earth's interior in terms of electrical conductivity. I think it makes sense to some extent. I don't know your background, but at the same time, I will try. You can put the questions, and I would be more than happy to answer those questions. Let me go to the next one. Now, it's a simple way. You can see there's a loop of current passing through that, and that gives rise to a magnetic field, primary magnetic field. And when it passes through the ground, that actually creates the eddy current. That's yellowish one. You can see the eddy currents, and the changing eddy currents create the secondary magnetic field. That means we can actually measure the secondary magnetic field on the receiver here. And if you look at one of the sounding, you probably are clear with the sounding. When you say the sounding means 1 point, from the 1 point, how much data we are collecting by looking at the depth region, deeper region. So that means the sounding gives you some responses from every layer within the Earth, from one point. So if you look at the sounding curve of one of these responses, it looks like that. You're seeing two different colors there, and the red color there, and the continuation of that along with the green color. This is actually a speciality of the system what we have used. It should have been just a continuous curve like that. But if you go for this continuous curve, and if you look at the x-axis, you can see the time mentioned there, going from few tenths of microseconds to few milliseconds. So that is the sort of responses we are looking at. And again, you can see over on the y-axis, you can see the dB by dt. That is a change in magnetic field with time. That's a change in magnetic field is a dB by dt. So that is actually looking at that responses. We can see that there's some sort of changes happening as the time goes. And this is a time domain response, EM response. And why these two colors? Because this one actually started on the very high frequency or very, very short time. That is few microseconds and to few tenths of microseconds, not millisecond. So we have two systems there. We can actually put the two dual system over there, and we can get the high area, that's very short time period, and also we can have the lower time period over there. And that actually gives you more information about the near surface layers of Earth and also the deeper layers. I'm talking about the whole thing can give you information about few meters depth to few hundred meters. I would probably say about 500 meters. Depends on the electrical conductivity structure of that region of survey. And another example over here, you can see how the responses are changing from another totally different one. This is an apparent resistivity curve. Once if we have this apparent resistivity with time, definitely we can convert that into the responses with respect to depth. So depth versus resistivity can be created from this apparent resistivity curve or the sounding. And how it looks like. If you look at that next one, you can see that there's a depth resistivity profile over here. It's from one sounding. Just one sounding, you can see it's actually there's a slightly about 60 ohm meter resistivity, and the resistivity changes, goes down, and resistivity increases further, and again it goes down about 100 meters or 120 meters to much lower value, and again it coming up gradually. So we are seeing a sounding curve for that. That's a depth resistivity profile from one set of measurement. That means just like one of these curves. This curve can provide you an information like that. So once if we get that information from one point, as I said, every few seconds a sounding is being done. When the helicopter is flying on top, we can make sure that every few seconds a sounding is done. Once if you have the sounding is done for few kilometers or few tens of kilometers, we can put them together. And we can put them together and represent in a different way. That is the next slide, I would say. You can see this area and different color pattern is given to that. You can see the different colors being given to that information what we are seeing on the responses what we getting on the EM responses. Once if we get the responses in the same pattern, similar way, we can actually go back to a depth resistivity profile at each point, each and every point. Again, depends on the speed of helicopter. Generally, this helicopter speed would be around 80 knots to 100 knots. So in that situation, we probably getting every few tens of meters one sounding. And this is a big profile, which is about 70 kilometers long profile. And this can be done in a few tens of minutes or maybe less than an hour. We can cover this whole area. So that's the way the survey can be done with the airborne system. So this color pattern actually gives you the conductivity in millisiemens. You know, the conductivity is the reverse of the resistivity. And generally we talk in terms of Siemens. And here we are looking at the millisiemens. So we can get much more clarity over there. And when we look at this particular conductivity section, you can see different colors. These red colors are corresponding to the high conductivity, and the blue colors are corresponds to the low conductivity. And again, you can see there is another layer, a high conductive layer continuously over here, right beneath the surface of the earth. And again, beneath that one, you are seeing a blue color over here. Can you see that? So, and again, there are patches of blue colors. That means low conductivity or high resistivity over here. And look at the thicknesses. The thicknesses varies from different places. So this information is just from one profile. If we have many profiles like that, we would be able to image the whole area in terms of electrical conductivity. And before getting into the details of that, I would like to share this particular slide with you. This actually shows you the resistivity or conductivity of different rock types. And this area is actually very low resistivity, and this is medium resistivity, high resistivity, very high resistivity, extremely high resistivity. So you can see it over there, and the other way around, you go down or over here, you can see the conductivity, just reverse of that. Very high conductivity and low conductivity, medium conductivity, and it goes the other way around, isn't it? So you're seeing very low conductivities over here, 10 to the power of -6, 10 to the power of -5 sort of things. So we are seeing, we have a scale of that from the geological measurements and also the lab measurements. We can have this, we can correlate that information with the sounding profile what we are getting from the airborne geophysics. Okay, so it's a combination of geology and geophysics. Then only we can make a meaningful interpretation for the whole thing. And right now, let me share with you the example of one of the surveys done for the Department of Water here in Western Australia. We are seeing the map of Australia. It's pretty big. It's I think 1.5 times of the size of India as a country, big one. And I'm showing this area which is marked. That area itself would be some of our Kerala, Tamil Nadu, Karnataka, and Andhra, at least that much. That's the size of this one, the whole thing. And we can go further down. We are seeing a small area right here. That itself is pretty big area. And you can see it's enlarged of that area with a 3D image of that. And this is the area of our interest or the interest of Department of Waters to do a survey. And the population over here will be very, very minimum. Lots of vegetation there. And only the main city over here is a Broome. Over here, probably you heard about the Broome city, a small city, of course. And then this area, this water over here, is a area of the big project. The Shell has a, the petroleum company Shell has a Gorgon project, huge project. So they wanted to have that huge project done offshore. And so everything will be run from this city, Broome, and that would government is expecting that more people would be moving to that area, and they need to find out infrastructure for them. So they are actually finding out the water, groundwater situation over there first. Can we survive there? Do we have enough water there? Or do we have enough aquifers there so that we have the storage there? That's the reason why it is. So I'm going to the next slide. We can see the key objectives of this survey to map the water resources of the Broome sandstone aquifer. That's one of the aquifer, the name, the Broome area. And to obtain the better understanding of the nature of the contact between the base of the Broome sandstone and underlying siltstone. The siltstone and the clay stone, they are all more clayey situations, and they can hold the water like, they can't percolate the water through it. It will be holding it. And identify the aquitard or the clay layer of the near surface. There's another layer I already showed you. There are a few layers over there, not just one. And also to create a map of the water table. and to study the geometry of the shoreline intrusion. And I can see from Dr. Suresh Babu's talk on Monday that he was looking at the submarine groundwater discharge from the coastal line towards the ocean. What I'm looking at here is the other way around. We are looking at how the salt water is getting intruded into the land. Okay, so it's totally different, the opposite direction, but we can see that. Let me go further. And by doing all these things, we can assist the conceptualization of the hydrogeology and determine the quality and the quantity of available groundwater resources for the benefit of the local community. Local community of there is the Aboriginal community, not the Caucasian people around. Mostly the Aboriginal communities, and they have their own monuments over there. And when we do the airborne survey, the interesting part is that we won't be touching any of their monuments and very sensitive issues over there. Like you probably heard about a year ago, Rio Tinto has got the license for exploiting or start mining in one area. Unfortunately, when they were doing when they started this project, they came across a cave of which has Aboriginal paintings, which is believed to be 50,000 years old. I don't know, but it is dated to 50,000 years. And so that was a preserved area. There is a big issue on that. So when we do this sort of things like airborne survey, we don't have to touch anything. We can actually get the full information. It's a non-invasive method. So we are not drilling, we are not touching the ground, but we are still getting the information, not touching the environment. Okay, so that is the main objective of the this survey, the example. And also this is some information about the geological settings over there. We know that there's a Broome sandstone over there, the aquifer is there, there's a siltstone there, there's another layer of aquifer there, and a few things over there. We are talking about few hundred meters. So I'm not getting into the geology of that region at this stage because you may not be familiar with that area. So it's no sense in going into details of that. So what we do when we go for an airborne EM survey, we need to calibrate the system first. Look at this hexagonal shape transmitter loop. Is a PVC pipe there, and the wires are passing through this PVC pipe. So make it sturdy. And we have a transmitter sitting right here. And we also have a bow over here, which actually can also accommodate under the magnetometer, if you wish. So it's extra information we are getting along with the EM information. And we have a transmitter there, and transmitter is actually hooked with the wires. So it will be right in the like this is the receiver over here and the transmitter there. Okay, so it goes like that. And how do we calibrate this system? We can actually pass the current through this loop while we are sitting there on the ground, and then we can do the measurement. So we get some ground responses exactly similar to any of the EM surveys, any of the time domain EM survey which is done on the ground. Some of you may be familiar with that. EM's loop, the transmitter loop is put on the ground, and we also have a receiver. Then we pass a current through the the transmitting loop, and then we get the responses on the receiver, and then we look at it, what we are getting, what is the noise level. All this information on the ground level can be found, and that is one way of calibrating it. And the second stage of calibration is that we are not making the measurement on the ground, we are making from the air. So can we calibrate air, the measurement in the air? How do we do that? We can do it. We can actually lift this one using a helicopter, and we can fly up, and then we get some high altitude test. It fly up to about more than 1,000 meters, 1 kilometer up. That means away from all the responses from the ground. So when I say all the responses from the ground means no noise from the ground is recorded at that height. When it goes there, whatever noise we are getting is the instrumental noises. So we can compare the instrumental noises, and we can get the ground noises, and we can assess them, and we can eliminate these noises in the beginning itself. once we are able to standardize or calibrate the system by doing these ground measurements and the high altitude test, we are ready for making the survey, doing the survey, so that we know what exactly is the responses from the ground. The range of responses, not the exact the ground, the responses, the range of responses what we can observe depends on the time, which time is good for us, which time band is the best data set we can use for the studying the subsurface geology. So when we go for it, we have the system. Look at that. When we lift it, it's almost like that. It's flying like this and it's horizontal. And there's a GPS system attached to that one on both sides and also over here, so that we can actually control. We can not control, we can monitor the pitch roll of this system. Pitch and roll of the system. Probably when Dr. Sunil was talking about the application of geophysics, GPS on earth sciences, probably he might have talked about such applications. So exactly that's what we can use here. So we are using it there. So we have the GPS systems on the wings over there, and so that we can find out the tilt. So in perfect condition, in the textbook style condition, it should be flat, horizontal, but it won't be like that because it's flying and it's at a height. So we don't have any control over there, but we can use the mathematical knowledge on the tilt and the heave and the rotations, so that we can correct it for that. So the correction can be done with the help of the altitude and the attitude of the system receiver, and the transmitter can be monitored and corrected using the GPS system. Okay, so we use that information, and when we look at this area, we are seeing lots of smaller lines and longer lines over here. This is actually the survey lines. We are talking about an area about this one line is about 70 kilometers. I'm talking about this one line is about 70 kilometers. And this should be more than 100 kilometers. And the small lines over here, it ranges from 5 kilometers to 20 kilometers. Okay, so, and the spacing, the line spacing for the longer lines is about 3 kilometers. Every 3 kilometers within the 100 kilometers, you have one line profile across it. There's one transect there. And these lines, the smaller lines, what we are seeing there, they are about 500 meters apart. The small lines are 500 meters apart. And why do we go for these small lines in the coastal region? Because we want to know about the coastal region, how the salt water is being intruded into the land. And in case if we are discharged, if we are withdrawing more groundwater from the ground along this one of this area, especially the cities over here, if they are drawing more groundwater for the drinking purpose or the their agriculture purpose, what happens? The salt water is getting gradually intruding into the groundwater system. That will spoil the water system. So they are monitoring that as well. So let us look at it, how they are going. We can look at it. Next one. So if we do the survey like this, we can actually get some responses, and the responses from the high moment and the low moment are there. So we have the super low moment, which gives you more information about the shallow region, and this one will give you the information about the deeper region. And this is actually the flight altitude. So we can do the corrections. Also, we have the other GPS measurements so that we can do the corrections for the tilt of the system as well. Okay, I think we are in track. So going further with that, once if we get all this information like what we have seen here, we can put all those information into the responses throughout the area. And if you look at the early time area, the responses, we can plot them in this way, each line, and some color pattern can be seen already. It's just the raw data. It's not the actual inverted data. It's the raw data can be clearly seen over there. See, there's a pattern there. And if you look at the deeper area, again, we are seeing another pattern there. The color is different, isn't it? So we are seeing that sort of responses from the raw data itself. Once the raw data is there, as I mentioned, we can go further with the data processing and inversion of the data. And we do different types of inversion for that. There are a few different methods which is mentioned over here. Is the high time is one of the laterally constrained inversion scheme in EM, and another one RHAS workbench is another one laterally constrained inversion by Denmark-based company. So we actually this system what we have used is called a SkyTime. I forgot to mention that. The SkyTime is actually developed by the Aarhus University based in Denmark. And so we had that collaborative work with them. And while I was working with the ground probe geophysics, that's the one which actually they're representing the SkyTime here in Australia and Asia region. So I had more interaction with them on that. So once if we get that information, then we get on to putting the 1D depth resistivity or depth conductivity and forms the big profile. You can see is one of the inversion scheme which provides that this information, and the second inversion scheme gives you a better information, laterally constrained information we are getting there. LIC, laterally constrained inversion. Okay, so we are getting that sort of information, and if you look at the scale over here, it's very clear that this is very low conductivity. That means 1 or close to 1 to 10. The color over there, you can see that. And over here, you can see the very high conductivity is more than 1000, is going up to this level. Is almost the level of the seawater conductivity. Can you see that? And from there, we go further. We will look at it further. And we have one more. Just looking at it. Yeah. We can see another line there. Here also we can see this side towards the coastal region, we have the red colors means high conductivity, and is going over there, the hilly terrain there, and you can see the low conductivity, could be a sediment or sandy terrain over there, and this is highly conductivity, could be a clay layer, isn't it? So you can see various layers there, but the constraints available, geological constraints available there is very minimum. You can see one of them, there is a drill hole over there. There's a drill hole mentioned over there. So they have some information over there, but not the whole area. So we have to look at that drill hole information also and compare that with the whole area. Look at that. We are doing some more profiles, big, longer profiles over there, and some patterns, the repeated patterns can be seen there. Some structural patterns can be seen there. And look at closely on this one. You are clearly seeing that this is the oceanic side there, and you can clearly see that the ocean water or the salt water is getting intruded in that region, isn't it? But there's a structural constraint over there, some sort of structural pattern there, which is actually restricting to move it that way instead of that is moving downward. Can you see that? So it's going like that. Let us go further. We can actually put this conductivity measurement into depth slices, like we are putting the bread. We can stack it together and we can slice it down. How does the slicing look like? Look at this one. You can see the top 0 to 10 meters depth. Different areas can be seen. And this pinkish color is very highly conductive region. There is the coastal region, followed by some areas of more conductive ones over here. And this area you are seeing less conductive. And when you go down further, it's about 40 to 50 meters, you are seeing some trends, some linear trends, some structural trends over there. And let us go further down and see the slices. Look at that. The shelf, the continental shelf or the margin region is getting like that. And again, still you can see some trend over there and some structural patterns over there still being persisting. And go further down, you can see that, and the whole thing can be put as a 3D model now. Let us look at a 3D model of that. So now look at it. We have the responses from all these lines, the depth conductivity profiles from each and every line, along with the lines of the very close line, the 500 meters close lines over here. And you can clearly demarcate the surface situation there. And from here, we can actually slice it down. How we can slice it down, let us see how it is. We are going down 10 meters, 30 meters, 50 meters down from the ground, 100 meters. See how the salt water is intruding over there. Can you see that? You're seeing it, how the things are changing over there. And you're seeing in this depth, about 250 meters depth, this whole area is actually with the salty layer. But still you are seeing some structural pattern there, and some structural patterns there, some structures there. And again, we can look further. We can remove all these things and look at just these conductivities, the top conductivities. And that actually gives you more information about the very highly conducting clay or the saline water situations. Look at that. We can contour it and we can get those information from there. And if we put this information onto the map of the region, that makes more sense to you. See that the land is there, the coastal region there, and we are seeing the seawater intrusions in this area. Okay, and once if we get this data, the whole data set, we need to compare this data with already available information. The Department of Water here in Western Australia, they didn't have that much of information with them, but they still had some drill holes here and there, and using the drill holes, they extrapolated the data and they made a groundwater table, contours of the map of that region. And here I'm showing the groundwater map which was produced by the Department of Water some years ago. So you can see that this is the lines, the blue line shown there is the groundwater contours, the maps of the groundwater level, the depth. And this line of this area, this is the one there, the survey area. So we are looking at this particular area. And if we take the profiles, the Department of Water's originally available profiles, you can see that they had a drill hole over there. There's a drill hole over here. There's a drill hole there, the drill hole there, and few drill holes. You can see the location of the drill holes. With that help of that drill holes, they actually made a hydrogeological model for that region. Of course, they are seeing the seawater intrusions like that. You can see the yellowish patch over there. It's actually showing the seawater intrusion towards that side, but with a very limited information over there. And from there, we need to look at our data. As I said, we have a line over here. We have whole line, whole area has been covered. So look at the sort of information what we are getting from the airborne data. Look at this. So that particular line, you can see that. But it's different from what they have predicted. But they predicted with very limited amount of data. But again, you are seeing a perched information over there. Can you see that? It's almost like a perched water table. And again, we can see the different layers, the seawater intrusions there. And there's a thick, low conductivity or the high resistive layer there. That's a sedimentary layer or the sandstone layer there. And again, when you compare these two, you can see that how it is. And some changes over there. And even here, you can see how the perched tables over there just beneath the ground level. And again, here is another one. And so when you look at the old image cross-sections, hydrogeological cross-sections by the department with limited data, this is actually the data which we have from the airborne survey, which is supporting them and giving you more information for that. So using that information and using that confidence, how do we get into further investigation on that? So we do the drill hole measurements. We can have the drill hole measurements. So as I said, there are a few drill holes over there. So drill hole locations have been marked like this. You can see that. And from there, we can actually get the in situ resistivity depth changes by using this sort of measurement. And the whole lines over there, they are actually from the airborne measurements. So we have something to compare with, or some a priori model, a priori information to compare the data we have collected. So using those information, we have done a map or a contour map or the water table, depth to the water table using the data from the airborne system. And also that helped us to look at the depth to the base of the Broom sandstone, the sandstone layer. What is the advantage of sandstone? There are aquifers, and this area, lots of rain is there, and the rainwater can be going down and it will be stored in the aquifers over there. So if you are able to map those aquifers properly, that means you are mapping the groundwater, the good groundwater over there, so that it can be used for various purposes. Further to that, as a geophysicist, we would like to go further investigation on that. And look at that, this is a total magnetic intensity map of that region. And total magnetic intensity can be made into different format, like we can process the data and we can get the first vertical derivative of the total magnetic intensity. And that clearly shows these lineations there. That means there's some structural patterns over there from the magnetic data, which we have already seen from our own airborne EM data. And similarly, we can also compare the regional gravity anomaly data. We can look at the gravity anomaly there is a high anomaly and low anomaly over there. And we can possibly compare these low anomalies with the areas of thick sedimentary layer or sandstones. That means high gravity means the rock types are different, and more solid rock type density is high, and this would be comparing with the low density. That means the sandstones which is not packed properly, so that has less density comparing to the compact rocks that can be clearly seen over there. And further, coming to the conclusion of that part, we are able to look at the water table, we are able to look at the saltwater intrusions, and we also mapped the thickness of aquifers, and we also found shallow impermeable layers which can hold the water in between, and also the regional and local structural features of that. And with this information, we have given to this information is given to the Department of Waters here in Western Australia, and they did further drilling of some suggested areas, and I had an opportunity to look at the data from the ground, the further drilling, and the perfectly matching with the information what we provided from the airborne system. So that is the main part of this talk. But also I wanted to introduce a few more things to you. And as a whole, Australia has been covered completely by different geophysical methods, and the data is open, publicly open. This is unclassified data now. Anybody can get it. And the specialty of Australia is that 80% of the land is blanketed by sediments, not just thin sediments, thick sediments, few 100 meters to few kilometers. That means when the Gondwana land, as the geologist knows, when it's separating and India moved northward, and Antarctica moved southward, and Africa moved westward, and Australia moved eastward. And that time, again, the processes are happening over there. Australia had undergone several times of submerging and into the underwater and coming up again, re-emerging. And that submerging situations, it has undergone lots of sedimentation. And 80%, as I said, 80% of Australia is covered by blanketed by the thick sediments. And otherwise, we should be able to see the rock exposures like what we see when we travel on the trains through the Karnataka and Andhra Pradesh, the rocky types over there. We are seeing all the rocks over there exposed, but in Australia, we don't see that rocks. But everything is blanketed by thick sediments. So we have to use different geophysical methods, the non-invasive methods, to get deeper information. And it's a mineral-rich country, and currently is again Australia has the highest amount, like probably one of the countries, top countries with the iron ore and also uranium and other minerals, even gold, and also the petroleum resources. So this country has been surveyed extensively, and I just wanted to show you some more information, like some of the data set available. And I'm sure that we also, back in India, we have this sort of data set with the Geological Survey of India, but it may be classified data at this stage. It's not publicly available, but as research students or the students getting onto that level, you may get access at various levels. But I just wanted to cover a few more things. You can see different types of data. It's a surface data, geological data, gravity data, radiometric data, magnetic data, and other information over there. And what I want to direct you is nothing but a set of gravity data, which actually can be applicable to India as well. Look at the next one. Here I'm showing the ground gravity data is plotted in free air gravity anomaly, and that's in microgals. You can see the colors and depends on the values over here. So there's a pattern. Geological patterns can be seen. The structural patterns can be clearly seen. And this very similar information I can get from the satellite data. This is freely available. This data set is freely available to anybody. And still you can see most of the structures are clearly seen there. And only the scale is a bit different. And again, I'm plotting in milligals, not the microgals. So this scale is different, but the color pattern or the structural patterns can be clearly seen. Compare that. And another one is the magnetic data, the whole Australia, and this is the airborne radiometric data. And you look at the colors, uranium is the bluish, thorium is the greenish, and potassium is the reddish color. And look at this region, the uranium thorium situation, and Perth is somewhere here where I'm pointing now, so where I live. And this country is mineral rich, but is all available further down, not just on the surface, a few hundred meters depth or further down. And again, look at this one, the geological units of and lineaments, which we generally look at. And we can see the different structures and the units over there. And similarly, I'm just directing you to the India. We are looking at India now. This topographic map of Indian region. You can see the Himalayan mountain chains clearly seen, and also the Western Ghat is clearly seen, and all the structural coastal region is clearly seen. We have the Chagos Lactive Ridge is clearly seen over there, and we also have the 90s Ridge is clearly seen there at the bathymetry, and also we have the Andaman and Nicobar Islands, and again going back down to the Indonesian region. Okay. And for you, students, you have this data available freely from Danish National Space Center. Anybody can play with that. But only thing is that you need to know how to extract the data for your area of interest. And I haven't seen many publications from India on this data, because this is, look at that data. We are seeing all the structures there. And I had the privilege to work on this particular region in my PhD program. And you can see a negative gravity anomaly over here. And that is actually related to a ridge called 85 degrees ridge. I did, while I was working with the Indian Institute of Geomagnetism in the 80s and late 80s and 90s, early 90s, we had many traverses across this one on the Samudra Manthan, that's a GSI vessel, and also Sagar Kanya, that's a NIO vessel. And also we studied this region. You know, this Barren Island, which was recently erupted, the volcanic eruptions. I had the opportunity to go very close to that region while I was working in IIG. So I had the opportunity to work on this data and model this data in terms of electrical conductivity structures. That is a part of my PhD thesis. And if you go further down, you can also see this Chagos, Lactives over here and Chagos over there. So you can see that hotspot and how it is moving up very clearly. And I'm taking you further down to compare that data. Just wanted to give some hints on the Indian data. That's the main reason why I'm looking at it. Look at that, these things. Can you see that correlation over there with the topography and the gravity, the free air gravity anomaly there? And again, when you look further, we can impose it on top of it. and you can see all the structures there. We can see the Vindhyans. We can see the Eastern Ghat. We can see the Aravallis. Everything, and also the correlation with the gravity of the region. And as you know, currently the Geological Survey of India is doing lots of airborne survey. And what I understand, last year they have covered almost 70% of Indian continent, Indian region, with the airborne magnetics by different companies. And the initial part, they had some data like this. Look at this magnetic data from our region, the southern part of India. And we can see some of the structures over there, lineaments over there, very clearly demarcated in the magnetic data. This is published data. And some of you may be knowing Dr. Anand in IIG Bombay. He is the author, and Dr. Mita Rajaram, again from IIG Bombay. They were the authors of this paper, and it's available. And that can be clearly seen, all the structures, structural pattern in South India. But now we have better set of data there. But they were all looking at just one set of data, that is magnetic data. When we look at the geophysical method or the physical measurements, we can't just depend on one parameter. We need to look at different parameters. That means we are looking an object from different directions. So we need to learn that how to incorporate all the available information into one area so that we can have a meaningful interpretation of the data. Structures. And again, look at this free air gravity anomaly of Kerala region. Look at that. And look at some of the structural patterns over there. It's just from the free air anomaly. And we can actually create the Boger anomaly from there. We can actually model it. We can then compare with these ones. That would give more meaningful results for that. Again, look at that. The magnetic gravity anomalies put together some of the structure patterns of South India. And look at this area, particular region. I'm just directing you to Kadapa region, Kadapa Basin. Can you see that clearly? And you know this one, Dharwar. Okay, area over there, and also the pattern and Achengovil shear zone over there, and other Palghat region there. You can see all these shear zones over there. And I'm just taking you further down to the same images, the published data, again by Anand and Rajaram. You can see all this information there. And this actually can be correlated with the magnetics and the gravity over there. And gravity has nobody has been using that gravity so far. And that data is freely available. But of course, we can only look with that sort of satellite-based gravity. We can only look at broader structures, the long wavelength structures, not the very short ones. So we still have the information. Look at that. All this information can be put there, and we can actually get more information from about Kerala, isn't it? Look at that Kerala region and how complicated and how fascinating structures we have over there. Right. Okay, I'm going further and putting it together, the structure over there, just for your information, just bringing your curiosity into such researches. And again, and just putting this. Of course, it's not comparable to that what we have here in Australia, but still we are in that direction, getting better and better in India in terms of geophysical information. And I would stop there. Thank you. And just ending the slides over there. And I'm sure that is a long one. It took almost an hour, I think. I'm sorry for that, the long one, more than an hour. And some of you might have got some information, but I'll leave it to you, and I'm happy to take any questions. Thank you.
Thank you, sir. Hello.
Hello. Thank you.
I'm speechless. That was a very professional and informative lecture. Thank you, sir. Am I audible?
Yes.
Okay. Doubts bring fear, and clearing it will surely be a relief. Am I right? So, dear participants, please let yourself in the chat box or by unmuting yourself.
Hello, I have a doubt. Hello, am I audible?
Yes.
Yes, you're audible.
Yeah, I am right now doing postdoc in NSYS. Okay, I'm interested. I just came to know about all these airborne surveys and all these things right now from sir. Um, I am fascinated by the information sir gave that data is magnetic data about India is available. Can you mention it once again, sir?
Yeah, Smita, that's the one
Yeah,
person, isn't it? Yeah,
yeah.
Smita, good to hear that you're doing the postdoc over there at SES and SS. And thing is that this institute called Institute of Geomagnetism, Indian Institute of Geomagnetism, based in Bombay.
Yes, sir.
Currently, it's a Panvel. You can search for it, and
Okay.
just Google, and you will be finding the address of that.
Okay.
And there you have, I think Anand would be associate professor, I believe,
Okay.
right now. So he is the person who is the main author of the paper. And that paper is actually available internet. You can search for Anand and Mita Rajaram, Anand and Rajaram on this particular one.
Mita Rajaram. Okay.
Mita Rajaram and Anand. Anand
Okay.
is from Kerala only. Okay.
Okay, sir.
So we have somebody
Okay.
there. You can actually talk to him, and you
Okay.
definitely can have access to those sort of data or information and work on it. Yes.
Sir, you mentioned about Danish something space data.
Yes. Danish space data, Danish National Space Organization, and they have this DNS 08. I'm talking about
Okay.
they published a data set 12 years, 13 years ago.
Okay.
And that data set is the speciality of that is you can't just download just like that. You need to
Okay.
create a script, maybe C or for transcript for that is actually somebody can guide you on that. And
Okay.
there is a way you can download the data you want. You can download the whole world, whole globe,
Yes,
or
sir.
you can use it for a partial region, a particular region.
Okay.
And if you're interested, I have downloaded this data, but I don't know how I will be able to share with you.
Okay, sir. Okay, sir. I'm interested in Kerala region. How
All right.
to explore more groundwater or water potential of Kerala region.
Yeah.
That's what I'm interested. So that's what I asked you. How whether it's possible for me to do download it, whether if it is freely available
Yeah.
right now.
But there is one limitation for the data when you go for groundwater exploration. Groundwater exploration, we are looking at very shallow region and also very short wavelength. The features what we are looking at is maybe 1 or 2 kilometers or less than a kilometer.
Okay, sir. But still, then we
From
can.
From the space data, what you're getting
Okay.
is maybe 3 kilometers, 4 kilometers wavelength features. But at the
Okay.
same time, you get an overall picture of it so that you can actually pinpoint that region and go for further investigation. Yes, of course.
That's what, sir. That's what I want to look into.
Yeah.
Just even if we get a vague idea about which location we have to explore more,
Yeah.
that will be more useful because right now Kerala is going more into summer drought.
Yep.
Even though we have a lot of water, surface water potential, but still January to May is in many of the rivers we are facing water shortage. So
Yep.
we should go for exploring more and more groundwater potential, and also coastal region is facing saltwater erosion problems. So I think we need to go more into geophysical investigation uh, to solve the problems related to coastal region, saltwater
Yes.
intrusion, and other things, sir.
Yeah,
That's what I
certainly.
was.
You're absolutely right. But remember that this gravity, what we are seeing now, or the space-borne gravity would only give you the structural information. But if you go further down with the gravity gradiometry,
Okay.
that's very expensive, but there is a method with which you can actually even look at the fluctuation of the groundwater level.
Water level. Is it, sir? Okay, sir.
Okay, so it can go.
Okay.
Yeah.
Okay. Okay. Yeah. Sir, your talk was really informative. In the point of view of Kerala itself, we have lot of scope for further research.
Yep.
We have to explore all these things. Anyway, I am new to this because I am basically a civil engineer, and but right now doing postdoc in water resources.
Yep. Interesting.
So I am new to this, but I am interested in more into geophysical right now because there is a lot more scope for that rather than running for the surface resources, which are right now going to be in a limited stage, even though climate change is offering many other changes and other things, which is not that much predictable. So,
Absolutely.
Okay, sir. Thank you.
Thank you very much, Smita. Good luck with your research.
Okay, sir.
Thank you, sir. I guess we have another question from Nanda Priya. So she's asking if there's any large difference between the methods used in Australia and India.
Absolutely no. Only thing is that currently we have lots of red tapes or the restrictions from the government side to implement any of the methods over there. Otherwise, whatever methods being used here in Australia are available in India also. But there's a difference. Only one difference is that the surface. If you look at the near surface features in Australia, we have sediments. Thick sediments is a thick conductive layer on top. To tackle that conductive layers, we need to approach in a different way when we approach with the area where we have exposed rocks. So certain signals, what we are finding back in Indian conditions, may be a noise for the Australian situations because we have a different geology altogether. With the top layer, the few hundred to few kilometers is thick sediments. So we need to look at that here. It's much tougher to do it here and much easier to do there in India. And most of these techniques have been well established in Canada and in America, US. And when these Canadian people came over here with their information and they were trying to implement it here, they found it was very difficult because the Australian situation was different in terms of the geology, that is the top conductive layer of sediments. Otherwise, everything is fine. But so we need to go through that first few hundred to few thousand meters of sediments before we hitting the rock. So there's a difference over there, but the same methods can be approached in a different way in different countries and different geological situations. Is that clear? Thank you.
Yes, sir. May I?
Thank you, sir.
All right.
Hello, sir.
So if there's
May
anyone, yeah, please.
Hi, sir. Myself, I'm Shabana Ibrahim. I'm a research scholar in MES Ponani College in the Department of Geology. And I'm new to the research field, and my topic is about Mars. And I have also to process the fluvial characteristics, etc., in the Martian surface. So my doubt is that whether can we, the presence of water is still a controversial topic among the scientists. Okay. So my doubt is that can we study the underground water presence or underground ocean presence in the planetary science using the satellites?
Right. So you have two statements. One is that the controversial situation with the presence of groundwater. That's one thing. What is one of the statements? Did you make it?
Yeah.
I think you have made that. And secondly, you are looking at the underground ocean situation.
Yeah.
That means, so if you look at the, that's actually your question. Again, the question goes down to the structure of Earth. And when we look at that, underground ocean means, are we talking in terms of the the normal ground level? I'm talking about the land and ocean. We know that the land is covered only about 28% and the ocean or the water is 72% of the globe. But from there, you're looking at some underground water underground ocean beneath the crust. Is that something?
Yes. Yes. Because currently there is no liquid water in Mars.
Yeah. Oh, in Mars. No, not on the Earth. You are not talking about Earth.
Okay.
I didn't
I'm
get
not talking about Earth. I'm
can,
talking about planets.
oh, right,
What
planets.
what
Yeah.
if can yeah? What if there are underground oceans? Can we study it using this satellite?
Underground oceans on the other planets you are talking about?
Yes, yes. Subsurface liquid or subsurface water presence
Yeah.
in the planetary in planets.
At this stage, the data what we are getting is actually concentrating on the Earth's side, but there could be some missions by NASA or from ISRO where they have done some research on the surface of Mars. I'm not very sure, but there will be some. All this information, if the techniques are already being, successfully implemented on Earth, there's no reason why it cannot be used in other planets. So some of these Mars missions, they had the geological and geophysical equipments on board. Smaller, minor, micro level 1, lower, scale will be very small, but they were taking the samples and they were looking at the resistivity also, not only just the geological part of it, also the petrogeological part. That means the composition of it. And if you know the composition of the rock types over there on the surface of Mars, definitely there'll some indication on the resistivity and other physical parameters. And I guess they have been doing it, but I don't have further information.
Yes, it has been identified the presence of hydrous minerals on the Martian surface.
So there will be
Yes,
certainly, that's a good area to explore, definitely, but very limited data available at this stage, isn't it?
Yes, very limited data because everything relies on the remote sensing, right?
Correct. Yeah, that's a
we
good.
We don't have access to the rock components or that raw materials from the surface.
Yeah. So still we have limitations, but that will be solved soon, I believe, because all these space missions are coming now, and it will be further up. I think Virgin is actually linking with the NASA for doing further research in Mars and Jupiter. So this sort of space technology, space research will be advancing soon. And
yes, so recently UAE and China has successfully landed missions on Mars. UAE's Hope and China's Tianwen.
Okay, so these things are there. So and so they get more data. Once if you get more data, definitely you have more information. And only thing is that, as you said, nobody has brought anything back from Mars. So we may have, but we don't need to have a look at like that. Nowadays, all the instruments, if you can send the instruments over there and they can analyze by themselves and get the data here. So there's no dearth for information. And certainly that would take to the next level. And being a part of research is always good. Well
Thank
done.
you, sir. Thank you so much. Thank you so much. And your session was very beautiful. You beautifully explained everything. Thank you so much, sir.
Thank you. My pleasure.
Okay.
Dr. Joman Joseph, may I ask one thing? While conducting the electromagnetic survey by Airborne, any vibration causing the movement of, trucks or any vehicle may cause your data?
You mean the vibration of the
earth movements causing by the movements of trucks or train or something like that?
Absolutely. There are a few things. One is if you are doing a survey in an area of high power lines, yes, it would have effect on it because we are actually sending current through that high power lines, and that would give their own magnetic field, and that definitely have an effect on it. So we need to have the ground information, definitely. And similarly, the railway lines, think about that. That also can have effect on it. So we can delineate these things. We can remove that from the data once if you know the ground truth of the region. So definitely these things would have an effect on it. Good question.
So can you compare the gamma metric survey data with your airborne survey?
Once again, please, can you repeat the question?
Can you compare a gamma metric survey for using for oil exploration,
Yeah.
So with your own survey?
Yes,
Airborne survey.
radiometric surveys actually being done along with, we can combine. We don't have to go separately for radiometric surveys. And instead of that, we can actually combine it with a magnetic survey easily and radiometric survey, EM survey. So EM survey, I showed you that big frame over there, the structure, that's a transmitter. We can actually put a spectrometer on it. We can have a spectrometer on the wings, and we can have the magnetometer on the tip. We can measure.
This EM survey maybe maximum 50 kilometers, can pass through.
EM surveys can be longer than that, depends on the what type of helicopter you are using. So 100 kilometers of length in a survey is fine with a helicopter. And if you go with fixed wing surveys, it is much faster, but it's flying much higher. Still, they can collect data. And airborne, this fixed wing system, like the systems with the fixed wing, have the transmitter, the EM transmitter on around the plane. That means the wings and the tail and the bow, and the sensor will be hanging. And inside the aircraft, you can have your radiometrics, and on the tip of the the aircraft and the wings, you can have the magnetic sensors, and also you can have the gravity sensor, gravimeter installed within the aircraft. And Fugro, that's a form of Fugro is the CGG. They have put all these multi sensors over there. So they have a aircraft which can have all the four type of measurement together done. It's possible. And another thing what we have to think is, when we have this EM measurements, we also need to consider the change in magnetic field of Earth. It's not constant, like the external field is changing every day. And sometimes we may get the magnetic storms or substorms. That's due to the solar flare radiations from the sun. So when you do a survey, EM survey or magnetic survey, we need to consider these events, but we can forecast it, we can monitor it, because around the world, more than 150 observatories, magnetic observatories, are measuring this continuously. So we can always forecast it, we can always get the information, we can always correct it for. Did I answer your question? Can you hear me?
Yeah, being a GMA geophysicist, what is your idea? What is your opinion about starting a MSc geophysics course here?
That's it.
Any wide scope for the employment opportunities?
That's a difficult question for me. When you look at our situation back in India, geology, how many graduates are getting into geological jobs or geology related earth science jobs after doing their masters at this stage? I don't know how many are there, because what I hear some time back was half of them would be going into IT side. Is that right? I can't hear you. Sorry.
Mostly they're doing on IT side with a specialized GIS and remote sensing.
Yeah. So in that way, so that way, even if you do the geophysics, but geophysics has a scope like always you have the physics part of it, and application of physics is there. So you are coming out with a combination of geology, physics, and maths. And for me, that's a good combination, strong combination. You'll be fitting into various things as long as you are affinity to physics and geology and maths, that goes together. And you don't need to get into very deep maths for this one, but the quite middle level maths expertise is enough for doing that, unless otherwise you are not going into the theoretical geophysics part. So, and job opportunities fluctuates. Here in Australia, the job opportunities fluctuates quite a lot. Every 5 years, you can see that it changes. So once if you, okay, for example, now we have a mining boom, if you say, and oh, okay, mining boom, lots of jobs around. And suddenly after 5 years, by the time the kids who joined or students who joined for the undergrad studies, when they graduate, it may be a mining, going down, and they may not be able to find job. That is not just Australia, I think it's a worldwide situation. All depends on the commodity prices. So, but learning this, studying this, if you have passion towards the subject, and it will take you in a better position. Anybody, no doubt about it. That's my experience with that. And job will come in your own way, and you will find a job on it. And you can apply this, information, definitely. Aisha may be thinking about it. She's a first-year student, and how to go ahead with that, isn't it?
Oh, so I was motivated actually.
Okay.
Any students with doubts?
Just one thing. I'm sorry that I didn't answer you, Professor Davids, because I'm it's still not clear with me whether how it will be going. Okay.
It's okay now. It's okay. Any students or any participants can ask anything about your future, about geophysics and a combination of geology and physics.
Yep, please.
Please ask. It's a golden opportunity to ask with such a senior scientist. Don't hesitate to ask. If not,
Sir, I think I have a doubt. It might not be so big, or sometimes it might be silly. So, well, the airborne platforms like you've shown are, the transmitters are hung down from the helicopters, right? So as we all know, stratosphere is also a part of a biosphere, and there might be birds, and all those animals, flying animals. So do you think there'll be any disturbances by them?
No, if they are disturbed by helicopter flying, yes, that disturbance. Otherwise, just the system, geophysical system is not going to affect any of their life, because it's only passing the current through that loop over there. So it's not going to affect that. But if it is flying in a populated region, is a noise pollution. Of course, noise pollution can be affected. Otherwise, there is no problem with that.
What about biosphere affecting the, transmitters, or like any disturbance in data collection?
No, this one's like especially this airborne EM system or magnetic system or radiometric system or gravity system, the transmitters are very limited. It's not harmful to any living organisms. Very limited, very minute. If at all there is any problem, it would be very negligible, extremely negligible situation. So, but if it is seismic, of course, it's a ground measurement, and it has the the exploding the things over there. You need to trigger the sound. So that is different. That has some effect on the ground, because any like reptiles or any of this can be affected by that. But airborne measurement, apart from that sound of helicopter flying right above you at a height of 100 meters, it's not that comfortable situation. Think about that. Helicopter is flying above you and hanging something, a bigger structure at about 30 meters, and flying on top of you. It's not comfortable. And
yeah, it's not.
Lots of sound. There are situations, I'm not joking, there are situations this was broken and the whole system collapsed, isn't it? It can happen.
That is sad.
Sad, but it can happen. And remember that there's a pilot on top of it. He only had to, he is trying to survive himself by dehooking that, releasing the system from the aircraft. Otherwise, he will also die.
Yeah.
Yeah. So he releases that, but these sort of surveys are not done in a populated region. That actually reminds me about a survey which we were conducted in, like we had the Fukushima earthquake and the nuclear radiations over there in 2011. So in 2012, there was a big project to do a survey around that region to monitor how the radiation is happening there, how it is being affected by various organisms and people over there, and also the sediments and the water. So they were looking at doing some surveys in that region, and nobody can go close to that. So the only way to do is the airborne survey. And when they did that, they were looking at various options. What should we do? And then the policymakers decided that we are not going to run any survey with the hanging stuff over there. So all the surveys were done by fixing the things right on the aircraft and doing the survey, not on the hanging stuff, because this is a highly populated region, Fukushima region. So they can't do that. And people objected that. Yes. So situations comes like that. And also I remember that I was involved in another survey, in the airborne gravity survey, looking at the Japan has lots of 152 different nuclear power stations, and they were dumping. They have the nuclear waste. The waste, most of this waste have been dumping into the deep ocean trenches. So deep in about, you're talking about a few kilometers, like 4 to 8 kilometers deep. So they find out exact location where they can dump it so that it won't come up. No way is going to affect the people. And we were actually in the process of making a helicopter-borne gravimeter system and testing it over there. And we are flying at about 120 meters above. And when we did the survey, we got the complaints from the city council. No, you are not supposed to do it. It's disturbing our people around. Absolutely. So we can't do these surveys where thickly populated. So in Kerala, we can do it in a very limited region only. Remember that we are thickly populated.
Yeah, that's true. Well, thank you, sir. So is there any students? I guess not.
Am I audible?
Yes.
Yeah. So I'm Padma. I'm a third year geology student. Actually, my question is not connected to our topic, but it's a random question. Can I ask you?
Please.
Okay. Do you believe in multiverse or parallel world?
That is a tough question for me.
Because I'm just like I love to like read some articles, and I love to read about parallel world. So I have to ask that. I mean, do you believe in multiverse? Or what's your opinion about multiverse or parallel world?
Yeah, it's something which I may not be able to answer. I'm sorry about that, Padma, because my knowledge on that topic would be very, very minimum. So I'm afraid if I make a comment, that may not be the useful one. Sorry for that.
Okay, thank you.
Sir, hello, sir. May I ask? Hello.
Please.
Is there any strata or structure or in underlying structure or strata which give a controversy profile in inversion profile in this data?
Can I ask you one thing? I got your question. Can you identify yourself? Your name?
My name is Naji. I am completed MSc.
And from where?
From Goa University.
From Goa University, you completed your MSc in geology?
Yeah.
And you.
All right. Can I answer that?
Yes, sir.
When you go for any inversions, any geophysical inversions, we are looking at the physical properties. Physical properties have not a definite numbers. We have a range, number range. When we go for the range, either in thickness or in conductivity or resistivity or whatever physical parameters, density or any physical parameters, we can't say that, okay, if it is 1 ohm meter, this is the structure, this is the rock there. No, we can't say that. we will be looking at, okay, this has a range of a density or rates of resistivity of that, and it has a density of that. It has a magnetic susceptibility of that. It has various other pattern features of that. Crustal structure is that. So put all these things together, we can come to a conclusion probably that is a particular mineral or particular rock. Otherwise, any physical measurement, it has its own constraints. We cannot make a geological interpretation with one set of data. It's like we are taking an object, we don't know what exactly inside there, and we need to look in different directions. It's like, you know, the blind people looking at an elephant, and one person is looking at the trunk, one at the trunk, the tusk, one on the leg, one on the tail, and they all have, and one on the ear. They have different impression about the elephant, isn't it? Similar way, we need to put all these things. If you put all this information together, you can see the elephant has a structure like that. Similar way, whatever is there underneath the earth, we don't know. We are all blind people there. We are all blind. So we are just looking at various angles, looking at various feelings of that. So geophysical feeling means conductivity feeling, or resistivity feeling, or density feeling, or magnetic susceptibility feeling, or sound wave propagation, that's a seismic wave propagation feeling. All these things have been put together, and also we look at get some some more, whatever information what we have, put them together, then probably we can come to a conclusion very close to that. That is sort of rock type or a layer over there. So any model has its own constraints. So we need to include or incorporate all the available a priori information into it to get a realistic model. So if you're doing a research, don't go for just one parameter and interpret the whole world. Put everything available and try, and also remember that you have a constraints on your model. Am I clear?
Yes, sir. Sure. Thank you.
Anyone else with doubts? If not, we'll be continuing. Well, I guess among all these 4 days, today was, I think students were very comfortable with you, sir. It was very friendly lecture, and we had the most doubts, and we were so open. It was really nice. So thank you, sir. Thank you all. It was a very friendly lecture, and thank you, sir, for clearing all our doubts. Well, now participants, I would like to inform you all that the feedback form is available in the chat box, and I request every participant to fill it for the certificates. Now, Maya Angelou said, be present in all the things and thankful for all the things. So I call upon my beloved friend Haripriya MS of the first year geology to express their gratitude on behalf of all of us present here.
Am I audible?
You are.
Yes.
Very warm good morning to one and all present here. It's my privilege to have been asked to propose a vote of thanks on this occasion. On behalf of Sahridaya College of Advanced Studies and Environ 2021, I would like to show courtesy to our chief guest, Dr. John Joseph, who spared his valuable time for the webinar to help us explore more about the topic, an investigation of hidden water resources using airborne electromagnetics. The session about airborne geophysical survey techniques, its objectives, and method to track seawater intrusions using it was very informative. Thank you, sir, for the wonderful class, and also for enlightening us about the beauty of Australia. I would like to express my profound gratitude to our principal, Dr. Matthew Paul Hooken, for the felicitation. My heartfelt thanks to head of our department, Professor Davis KJ, and other faculty members who made this event a great success. Finally, yet importantly, a great appreciation to all the participants who attended this webinar with inquiring mind and made it a successful event. Once again, thank you all for your presence and participation.
Thank you, Haripriya. And thank you, sir. 30th of July 2021. It hurts to say, but it's the last day of Environ 2021, and it's tomorrow. But trust me, another full day of wisdom. What's more important and happier? I'm so happy to inform you that respected Dr. V.A. Aisha, head of the Department of Geology, MES, and honored Trivikram G, Director of Programs and Geoinformatics CED, Trivandrum, will be joining us for the event. The most awaited lecture, Satellite Applications in Coastal Zone Studies, will be given by our admired principal scientist at Satellite Application Center, ISRO, Ahmedabad, Dr. Ratish Ramachandran. After a good night's sleep, we'll open the doors of wisdom at the same time, 9:30 in the morning. So stay tuned and have a nice day. Thank you all.
Thank you, Aisha, for the wonderful introduction. Did well. Thank you.
Thank you, sir. Thank you.
John Joseph, thank you
Yes.
very much for pleasant and interactive sections. Thank you very much. Convey my regards to your family members, especially your wife and children. Okay.
Thank you. That is my pleasure to join the whole kids. Happy to hear that. They enjoyed it. And yeah, I'm available anytime if you want further information or further talks. Not now, maybe later stage, in case if you want. We'll think about it. Okay. Yeah. Thank you.
Anyway, I think all the participants are enjoyed these sections.
Okay.
Thank you. Thank you very much.
Thank you. Is that okay if I leave?
Yeah.
Yeah. Thank you.
Bye.